start streaming. All right, so a few things that are kind of important. First thing is you might see exam 1, question 1 being graded. You may not see it being graded because I'm in the process of grading it. So one half of the class may see it. I think I'm at person 26 out of 51. So almost exactly one half of the class will see a score, and then the other half may not see a score. So if you don't see a score for exam 1, question 1, do not be alarmed. I'm in the process of doing it. It is extremely, let me see how I should put it, numbing. When you're grading the same question like 50 times. So the first 10 is kind of fun because I get to see all the different wrong answers. And then it's just repetitive. It's like, nope, same thing that was with that one, or it's correct, wrong, correct. So it takes me a little bit of time to get through all the exams. Just try to be patient with me. So are there any questions regarding that? Okay. All right, so let me get to the lecture for today. Oh, and also the homework assignment for today. Okay, so we'll go ahead and talk about the solution of that homework assignment. And also, kind of spend some time to go back and look at why this homework assignment is significant, what kind of concept is trying to tie together, because I think that ultimately is what the assignment is really supposed to do. So we'll go ahead and do that today. So are there any questions other than the exam grading and also the answer to the homework assignment that was due today? Okay, no questions. All right. So in that case, I'm just going to go ahead with the homework assignment first. So this is your homework assignment, and I'm just going to double check and make sure that, oh wait, it's not due yet, so I cannot talk about it. It's due midnight tonight. So that means, for those of you who are thinking, oh man, I'm almost getting it done. Well, guess what? You have another 8 hours, a little short of 8 hours, to get it done. So I cannot talk about it, I cannot talk about the solution at this point, but I can still talk about the concepts in general. Okay, so that's the important part. All right. So in terms of the concept, because I got asked a few questions, during my office hours today, so it is important to understand, the concepts and how the concepts relate to each other, because there are a few concepts that this particular assignment, kind of brings together. So the first thing is, where's the notes? Where's the module? Okay, this is all about propositional logic. So make sure you know which module is responsible for the material for this homework assignment. And if you don't have time to go, okay, I got 8 hours or 7 hours and some 50 minutes, I don't have enough time to read through the whole module. So if you do not have enough time to do it, I would say start with Section 5. Okay, Section 5 talks about resolution, and I would say everything that you need to know to get the homework assignment done is probably starting from here. Okay. There are 3 concepts involved in this assignment. The first one is CNF, conjunctive normal form. The second one is the mechanism of resolution. The third one is a proof technique that we know as proof by contradiction. So those 3 concepts are interconnected in some weird way that makes up for the homework assignment. So before you even try to approach, okay, so what are those 3 concepts? How do they relate to each other? Think about why are we even in this topic? We want to prove theorems. We want the computer to be able to prove theorems. That's what we want. Okay, so understand the objective first. Okay, that's where we want to be at. So the next question is, how do we express things? That is where CNF, or conjunctive normal form, comes in handy, is how do we express things that we know are true already, as well as the theorem that we want to prove. So we want to express both of those, okay? things that we already know is true. So for the homework assignment, okay, I'm just going back to the homework assignment for the time being, because I can point these things out, without actually disclosing the answer. This part here is reflecting what we know is true. Okay, what we know is true are these two. Is this one single CNF, which has two disjunctive components. We know this is true. So the next question is, what is the theorem? What is the condition or the statement that we are saying, is this a theorem? Does it follow the things that we know are true or not? There are two parts to this homework assignment. The first one is T implies S and R. That is the first proposed theorem. Okay, doesn't mean it's a theorem. You have to tell me whether it is or is not a theorem. The second one is Q and R implies T. That is the second condition that you have to show me whether it is or is not a theorem. Is that part okay? Okay, so CNF is nothing more than a representation, because in the previous homework assignment, you saw how we started off with something that it does not even come close to a CNF, and then going through Boolean algebra, we were able to convert it into a CNF. Okay, so CNF is really just a representation. Any Boolean expression can turn into a CNF. Second thing, resolution. So resolution is a mechanism. It is a mechanism which is more or less, you can kind of look at it as a syntactic transformation. The syntactic transformation is, I think I might have that as a syntactic transformation here. There we go. So the syntactic transformation basically says, if you have a disjunctive term that looks like this, okay, we have phi or psi. You have another disjunctive term that looks like the negation of psi or rho. Now, what can be phi? Anything, okay? It can be a huge disjunction by itself. It can be just false, okay? 0 is false. So phi and rho, they can be anything. What we really are interested in is what is psi and what is not psi. So in a conjunctive normal form, psi can only be a variable, and then not psi becomes the negation of a single variable. Is that part okay? Okay. So what if we find two disjunctive terms within the conjunctive normal form such that they share one single variable, where on one side it is not negated, on the other side it is negated? What can we do about it? Well, the transformation says we can concatenate. Okay? But in the concatenation, which is basically the same thing as making a longer or bigger disjunctive form out of the original two, we can get rid of the variable that is negated on one side and non-negated on the other side. That is gone. Is that okay? So that is the syntactic transformation of resolution. Okay? It is based on a theorem, okay, but the homework assignment doesn't ask you to prove the theorem itself, and I have gone through that proof already. So your focus is not why it works, but to apply it so that you can use it as a tool. Is that part okay? All right, so we got two pieces done. We got CNF, which is a representation. We got resolution, because resolution only works in CNF, and that is why we need to represent everything as a conjunctive normal form, is because resolution depends on that. So now we have representation, some kind of random transformation. What is the third component? Proof by contradiction. Okay? What is proof by contradiction? So proof by contradiction has its own proof, which is down here. But the important part of proof by contradiction is this part here. So I'm just going to highlight or point to the part that is actually super important. So in this particular, on the last row, psi is representing a CNF that is everything that we know is true. Okay, so everything that we know is true is now combined into psi, which is a CNF itself. What about this thing here? Phi is a proposed theorem, a conjecture, okay? It's just a condition, a Boolean expression that we do not know whether it is a theorem or not, okay? So the question is it a theorem or not? If phi really is a theorem, okay, then the conjunction between everything that we already know, which we represent as psi here, it is its own CNF, and the negation of the theorem, the negation of the proposed theorem, the conjunction of these two implies false. In other words, it is false. Is that okay? Because what can imply false so that the implication itself is still true? There's only one thing that can imply false, such that the implication itself is still true. What is it? It's false itself, okay? So we need this thing to be false, or prove that it is false. But how do we prove psi and the negation of phi to be true? Resolution. But how does resolution work to that goal? That becomes the biggest question. So I think the most useful thing that I can express here is to tell you about the implicit disjunction that exists in every single disjunctive term. So this may be the most useful thing that I did not emphasize in class, but it was otherwise implied. Okay, so let's say we have P. Okay, so let's make this a little bit more fun. P or Q, and not P. Okay, so let's say I have a very simple CNF looking just like that. Okay, so how do we do a resolution? Well, it looks like on one side we have P, which is the non-negated variable. On the other side, we have not P, which is the negated version of the same variable. So it sounds like resolution is possible. But how do we resolve this? Because not P is all by itself. What do we concatenate that thing with? That becomes the question. Well, guess what? Every single time you see something as simple as this, you can always attach that. Because, anything or false is just that anything to begin with. Is that okay? So now we have a quote-unquote proper disjunctive term on both sides. So what do we do? Okay. Using resolution, we basically say this thing implies the following. It implies the concatenation of both of those expressions, but with P, not P removed. Okay. From the first disjunctive term, we got Q, which is coming from here. And then from the second one, we got the false. So we got that much. Is that okay? But anything or false is just that anything to begin with. So this is really just Q all by itself. So now what do we do with Q as an expression? We append it to the original CNF. Okay? In other words, we can now say that our CNF, okay, this is our original CNF. We can now say that this CNF is really saying the same thing, okay, as P or Q and not P, and this time we can append Q by itself. So now we have three terms in the CNF. It is very important for you to append the derived disjunctive term to the end of the original CNF, because whatever term you have derived can interact with other terms that may not have a chance to resolve. So that new term that you have derived needs to be appended to the end of the original CNF, so that CNF gets longer and longer and longer. So are we doing okay so far? Okay. In this particular case, can we resolve any further? In other words, if you look at P or Q, and not P and Q, can we resolve and get a new term out of these three? You can do it systematically. Look at the first versus the second. We have done that resolution already. Question? Yes. Okay, so how do we resolve and make a new term? They do not resolve. Okay, so these two, the first and the third, do not resolve because they're both non-negated. You need one to be negated, one to be non-negated in order to resolve. Okay, yep.
Could we, instead of appending to the end, if we did not do that and we replaced what we are implying with into the original expression, we ran into a contradiction, is it still valid?
As long as you can still run into a contradiction, yes.
It will be counted as correct.
It will still be counted, correct. Yep. All right. So if this is the CNF, which is the concatenation between psi, everything that we know is true, and also the negation of the theorem, we are now stuck. There are no further resolution that we can perform, and yet we cannot conclude with a zero. What does that mean? That means the proposed theorem, whatever it was, is not a theorem. It is not implied by everything that we know is true. Is that okay? Now, there are a few things that you need to watch out for, okay, especially for people who want to kind of do things quickly, okay? So if you look at something like this, you go like, oh, can we just do one single resolution because P, Q are both unnegated on one side and they're both negated on the other side. Can we combine that? The answer is no, you cannot, okay? The reason why you cannot do that is because if you treat P or Q as one single expression, the negation of that is not P and not Q, not P or not Q. So that is why you cannot look at this and go like, oh, we can go straight to zero. Nope, we cannot. So if you do it one term at a time, we can see what we can come out of what can come out of this one. So we can look at PQ, not P, whoops, or not Q. And I can choose which one to resolve first. Let's say I resolve P, not P first, okay? So what do we end up with? We end up with Q or not Q if I choose P to be the term that I use for the resolution, okay? But that is useless, okay? This is useless because what is Q or not Q? It's just one, right? So we now end up with P or Q, not P or not Q, or one, and one, okay? And then you just get rid of the one because anything and true is anything. So now we end up with P or Q and not P or not Q. Oh, we haven't gone anywhere. So what do you do next? Well, you can try to resolve using Q, but you end up with the same situation. So that means this original CNF is already done. We have hit a dead end. It cannot resolve any further, which also means we are not getting to the contradiction, which also means whatever the proposed theorem was is not really a theorem. Is that okay? More or less? Okay, yep.
In your notes, like in the proof by contradiction, and there were two examples.
Mm-hmm.
First one, basically, you said since because when we add to the CNF the proposed formula,
Mm-hmm.
It happened that we basically came back to the formula.
We cannot. There's no new term they can resolve to.
Yeah.
So in the notes, I have the exercise portion has two examples. Okay, well, actually, there's an example portion here.
This one, yeah.
Yeah. So this is the negation of the theorem, and you use the negation of the theorem and everything that is known to be true to make a longer CNF. You look at this particular CNF and you ask yourselves, can we perform any resolution? Now, the most systematic way is to say, can we resolve between the first and the second? Nope, because they both have the negated version of P, so they cannot resolve. First versus third cannot resolve. They don't even share the same variables, okay? First versus last, okay, cannot resolve because they both have a negated version of P. What do you do next? Look at the second one. Look at the second one versus the third one. Cannot resolve because they don't even share a variable. Second versus fourth Cannot resolve because they only contain the negative version of P, so you cannot resolve. Look at the third versus the fourth. They don't even share a variable. I have looked at every single possible way of pairing up the disjunctive terms, and yet no two of those disjunctive terms can resolve. We're done because there's no new term that we can resolve to add to the whole process. So we are stuck, which also means we cannot get to the contradiction that we're looking for, the zero. Then it means whatever the proposed theorem was is not a theorem.
Yeah, so can we just say like invalidated, for example, like as you said, like over there?
You just basically say we cannot get to a false, we cannot find the contradiction, and as a result, the proposed theorem cannot be proven as a theorem. Or you can just say it's not a theorem if you want to make it short. Is that okay? So the second example is actually a theorem. So in the second example, phi prime is P implies not Q, which means the negation of that theorem or proposed theorem becomes just P and Q. Now P and Q is in conjunctive normal form already. So we make a conjunction or bigger C and F based on that. So the first row here is I'm using underline to indicate what term I'm using in a resolution. So on the second row here, not P in the expression not P or not Q, and also P by itself, which is implicit in P or false, okay? Those two terms were used in the resolution. So you concatenate the rest, right? When you concatenate the rest, the first disjunctive term contributes not Q. The second disjunctive term contributes a 0. So now you have not Q or 0. The or 0 is just simplified out, and that's why we ended up with a new term, a new disjunctive term of not Q. Now the important part of adding this one to the entire thing is because ultimately this not Q is resolved with this Q here. Okay? So the conclusion of a 0 in this case has nothing to do with the interpretation of an expression and the negation of the expression is false. It really is just applying resolution blindly. It is a syntactic operation as opposed to a semantic operation. I do not need to know the meaning of and. I do not need to know the meaning of not. It is just the mechanism itself giving me this 0 here. Yep.
Why did you start with the second term instead of the first? Because there's a not P in the first.
No, I'm just choosing something in random order.
Okay.
So if I use the more systematic way, then it would have, look at this one and then check, and then check, and then check like that. Yep. Question? There was a hand. Yep.
Yeah, that's in the rectangle. How did you get that first line?
You mean the second row or this line here?
Right there.
Which one?
Yeah, that line. Where did you get
The first row.
the first one?
How did I end up with that? Well, we combine psi. Psi is this portion, and then we have the negation of phi prime, which is this portion. That goes back to proof by contradiction. When you have a conjunction of everything that is known to be true and the negation of a proposed theorem, if the proposed theorem is in fact a theorem, then you should end up with a contradiction, which means it is false, which we do end up here in this case. Is that answering the question or not? The derivation of psi and not phi prime is done a little bit before this. Yep.
If we do a resolution, can we do a resolution, for example, of not Q or not R or T and Q?
Yes.
Yeah.
Yep.
Is it going to be the result of it is going to be not R and T, right?
It's basically everything in the first one except for the not Q.
Okay. Yeah.
Because the not Q is annihilating the Q, so those two are gone. And then the Q has nothing else in that disjunctive term, so the first disjunctive term will just have not Q removed, and that becomes the result of the resolution. Okay? So are we, yep.
On the notepad again,
Uh-huh. Mouse pad.
Mouse pad.
Yes.
No, if you had so P, that's line 6.
Uh-huh.
So P and Q. Wait, no. What's the end sign again? Is it or?
The plus is the or, and then the multiplication is the and.
So P or Q and
Uh-huh.
not P or not Q. What if you had an actual like P or Q and then the actual negation of that? Would that be a contradiction by itself? Like if you had not P.
Then it's not disjunctive. Then it's not a CNF anymore. So you're talking about a negation of P or Q, right?
Like the actual negation of that.
Yes. So in that case, yes, they can resolve to 0, but that original form is not CNF to begin with.
Okay.
So that's why, when everything is in CNF, you can only resolve one term at a time. You cannot combine terms when you're resolving. All right. Any other questions? No other questions? So you have 7 hours and 30 minutes to turn it in. Just to keep that pressure up. All right. So both of these two things are done. And, yep.
So is the part that we derive and add to the original statement, is the original statement just what they were given, or what previous CNN?
Well, that's a good question. So I think last time we kind of talked about this a little bit. I think it's faster for me to just kind of write it. So I'm going to do it on the tablet. And I think I use one of these tabs here. Nope, it's this one. Okay, there we go. And may not be that one. Okay, this is 418. Okay. All right, so last time we talked about this a little bit. So let's say you have a disjunctive term. A can be a huge disjunctive term and B can be a huge disjunctive term, but A and B together is conjunctive, right? This is CNF. Is that okay? So A is basically just a placeholder of a potentially gigantic disjunctive term. It's a big or. And then B can also be potentially big, a huge, gigantic, disjunctive term, which is basically an or. Okay. So now the question is, what if I also know? Okay. So this is known to be true. So this is known to be true, and on top of this, we also know that A and B implies C. Okay. So when you combine these two, what can we say? So the question is, does that also imply, okay, question mark here, does it also imply A and B and C has to be true? Now, we talked about this last time already. What do you think? It is true, okay? So A and B is in the original CNF. A and B implies C is the result of resolution, okay? So after the resolution, whatever the resolution comes up with as a result, which is C in this case, you can attach that or append it to the original CNF. So I'm not sure whether I'm answering your question or not. It is? Okay. And that's basically what I'm doing in my own example right here. So that's why you can see the original CNF only has this many terms, and then we added not Q, and then we added 0. So every time I perform a step of resolution, if it comes up with a new term, I just append it to the original CNF. All right. Are there any additional questions about the homework assignment? This is all good? All right. Well, if you do come up with some questions, just let me know, as long as we are still in the lecture time. All right. So that part is done for now. And we can now continue to talk about the terms that we have talked about so far with counting. So I think last time we Okay, I just. Okay, so I think last time we kind of talked about this. So now the question is, okay, I think I tried my best to illustrate an example, with how to expand the omegas. So have you guys done any studying or try to do this yourself? No? Okay. Well, let's do it in today's class. Okay, so this is the first thing we'll do, which is good for reminding you what we have been talking about, and also to kind of expand this topic a little bit by giving you an actual example of how it works. Okay, so what we'll do is we'll switch to the tablet, and then we'll say, let's try to come up with omega 3 of the set A, B, C. Okay, I think that's easy enough that we can actually do it by hand. Okay, first of all, what does that mean? What is this omega doing here? What is the 3 doing here? What is the set as a parameter doing here? Okay, so I need you guys to help remind me. Just pretend that I am new to this class, I didn't study over the weekend, and I totally zoned out during class. So tell me again, what is omega, what is 3, and what is that thing inside, what is the curly brace stuff inside the parentheses? Yep. Omega is the set of outcome, and then the 3 is
Is the trial involved? Or no, how many trials?
the number of trials in the experiment. And what about that curly brace thing inside parentheses?
Those are the parameters that you have for the trials.
Okay. Those are the choices. Exactly. That is the set of choices for the first trial of the experiment. In other words, together, this is omega is saying this is the set of all possible outcomes of an experiment. Tell me more about the experiment. It has 3 trials. Okay, that's what the 3 is. We got 3 trials without replacement, which means once you take something out, you do not replace it. What about that ABC thing in curly braces? That is the set of your choices for the first trial. Okay, so that's what this means. Okay. So according to the equation, we now expand this and say, okay, what does it look like? If we pick out A first as from the first trial or trial 0, then we can say, what can A from the first trial pair up with, for the entire experiment? That's where we come up with the Cartesian product symbol. Okay? Because what are we combining it with is the following. It is basically all the potential outcomes of a smaller experiment. In other words, I'm saying, okay, I'm responsible for the first trial. I decide that A is what I have chosen for the first trial. Then I have to say, well, if I choose A for the first trial, what can this A combine with as the outcome of the entire experiment of 3 trials? But I'm too lazy to figure that out. So I'm going to ask somebody else to do it. So this is the somebody else. So the somebody else that I'm going to ask is to say, hey, you're responsible for a smaller experiment. It only has 2 trials. Okay? That the other person says, okay, fine, I'll do an experiment with 2 trials and tell you what the possible outcomes are. But that person also needs to know, so what are the choices available to me? Well, I cannot say A is available because A is already used. It is without replacement. So the person who's responsible for a 2-trial experiment only has ABC minus A available. So I can just say BC, but that's not the best way to do it. The best way is really just to say ABC minus A, like so. Is that making any sense? And then and then this person comes back, with all the possible outcomes of an experiment of 2 trials, only having B and C as available choices for the first trial of that sub-experiment. So I got all that stuff and go like, yeah, these things can combine with my first choice of A. But guess what? I can also choose B for my first trial. Okay, so what if that happens? Okay, if I choose B as my first, as the outcome of the first trial, then I have to ask somebody else, because I'm very lazy, and say, okay, you figure out the possible outcomes of a sub-experiment with only 2 trials. And then that person is going to ask, okay, so what can I choose from? I cannot use B again because I have, well, the other person cannot use B again because I have used B already. So from the other person's perspective, it will be ABC as a set minus what I have chosen for my first trial. And of course, the last one is just that. If I choose C for my first trial as the outcome of the first trial, then the sub-experiment is not going to have that available. Is that okay? So do we have any questions about these 3 components of the outcomes of a trial, of an experiment that has 3 trials, and the first trial has the choices of A, B, and C? Yep.
Would those 3 components be part of a larger set?
You mean these 3?
Wrap all 3 of those components in one single set?
Yes, we have to somehow combine them. But the question is, do we have any questions about those things as components? Well, okay, you're absolutely right. They are components of something. How do we combine these components? Okay, first of all, what does each one give me? In other words, if you're looking at a Cartesian product, and a Cartesian product here, what does each Cartesian product give me? A set, right? So now I have 3 sets as components. What can I possibly do to these 3 sets to kind of combine their results? Yep. Union, because we want to combine everything here. So if it is in here, or in here, or in here, they're all going to be a part of the possible outcomes of an experiment of 3 trials, and A, B, and C are available for the choices of the first trial. Is that making any sense? Then the next question is, we look at this and go like, what is that going to do? So the next question is now saying, what about omega 2 of B, C as subcomponents? Well, we're going to do about the same thing, right? This is about the possible outcomes of an experiment that has 2 trials with B, C as the choices of the first trial. How do we figure out all of these outcomes? Well, I guess we can choose B as the outcome of the first trial. But if that is the case, then we end up with a smaller sub-experiment that only has 1 trial left. And that trial only has B, C minus B as available choices for its own first trial. What if I do not choose B, instead I choose C for the first trial? Well, it's kind of the same thing. I have a smaller sub-experiment with only 1 trial, and that particular experiment has B, C minus C, because I have chosen it already, as choices. And once again, we have a union here. What about omega 1 of C? Well, that is just whatever set I'm given with, because omega 1 of the set C is asking what are the possible outcomes of an experiment that has 1 single trial, and then the choices for that 1 single trial is just one particular element called C. Well, I guess I don't really have a choice, do we? So C has to be the only possible outcome for that 1 single experiment. So do you see how the recursive definition works? Is that okay? All right. So I think this is kind of where we left off last time. Yes?
Don't we have to do also omega 2 of
Oh yeah,
for example,
yeah. I'm
AC
just,
and blah, blah,
but
blah.
it's going to look about the same, right? So if you look at the second one here, B is the one missing, so you have AC here. So you have AC here, and then you have AC, AC, and then AC here. So it's going to be about the same thing. But the idea is to break a big problem into smaller pieces, where each smaller piece has a resemblance in terms of nature as the original problem. So do we have any questions about this part? Because this is going to be your next homework assignment, is to write a program to generate all the possible outcomes, kind of like this. Yep.
So, just for going with the first A being chosen, and then the second, and then the final one.
Uh-huh.
The output for that chain would be two sets, A, B, C, and then A, C, D?
Not exactly, because each time it's using a Cartesian product, right? So we know whatever is coming out from this part is going to be a tuple that starts with A. Whatever is coming from the second one is going to be tuple starting with a B and tuple starting with a C.
Could you write out the answer for the zeros?
Sure. Okay, so we'll just focus on the A's. So that means, okay, so we know this one already. Okay, is that okay? All right. So that means I can plug all of those things back here, right? So omega 2 BC is going to be a set of BC as a tuple and CB as a tuple. Is that okay? Is that okay? So we now plug this back into here. So that means the first row of omega 3 is going to give us two 3 tuples. The first 3 tuple is going to be ABC as a tuple, and then the second one is ACB as a 3 tuple. Is that okay? The second row is going to give us BAC as a 3 tuple, BCA as a second tuple. The last row is going to give us CAB, CBA as 3 tuples. So is that working or not? Or less? Okay. I think this is also why 430 is listed as a co-requisite for this class, because I'm suspecting in 430 we should be writing recursive subroutines already. Is that about right? In the data structure class, are we touching on linked list? Search?
No, search and sort. Binary search.
Searching and sorting?
Yeah.
Those can be done recursively.
Yeah.
Just because we are stuck with searching and sorting is no excuse not to introduce recursion. Okay, I can see a few faces going like, what are you talking about? Search, we have to do it in a loop. No, we can do it in a loop, but not necessarily. Okay, so I'm going to touch on that a little bit because I really need to convey the concept of how recursion is useful in computer science. Okay, so let's say you're writing a C subroutine. Okay, so this is strictly a C subroutine, and you basically say, find. Okay, and the parameters is one is k, which is a key. This is the value that you're trying to look for. The second one is the array. Okay, so we'll say this is an array. And then the last one is the length of the array. Because in C and C++, you cannot find out how long an array is, unlike in Java and most other programming languages. So here we have the length itself, which is how long is A. Okay. So typically the way you do this, okay, without using recursion, is to say, okay, we'll introduce I as an index. And then you say for I equals to 0, I is, okay, in parentheses, I is less than len, which is the length of the entire array. And you also want to say that as long as I haven't found it yet. So you have to say, a bracket I, okay, a bracket I does not equal to k. And then if you need to go back to the array, the post operation is incrementing I, so you move on to the next item. And then there's nothing else to do. Well, that's the really cool thing of using a for loop instead of a while loop, is whatever you actually need to do can now be absorbed in the post operation. Okay, so if that is the case and you're supposed to report back whether you found the item or not, what is the return value? So what are you going to return? You cannot be returning any of the variables or parameters by itself. It has to be a relationship between certain things, right? So you have to think about, how am I going to exit the loop? There are two reasons why you can exit the loop. What reasons are those? Yep. I is less than len is the right, it's the condition to put here. But to get back to my original question, why can you exit the loop? There are two reasons why you can exit the loop. You can exit the loop when I is no longer less than len. Well, if I is not less than length, what is that telling you? I have seen every single element, and yet I have not found the value that I'm looking for. Okay, so that is telling you, if you exit because I is not less than length, that means you have not found, you cannot find the element in the array that has a value of k. But since I said the subroutine is supposed to return whether it returns true if and only if you find an element in A that has the value that you're looking for. So you can either do the negation of that, which is A is less than len. You have to do it. You cannot use this part here. So the answer is just, I is less than length. So this is a quick and easy linear search algorithm, assuming the array doesn't even have to be sorted, because it's just a dumb, exhaustive search through the entire array. It doesn't even have to be sorted. Is that okay? But I look at this and go like, it's not recursive. Let's make it recursive. So how do we make it recursive? In other words, how do we break a bigger question down to a smaller question of the same nature? In other words, I am not changing any one of these parameters, because I want the recursive version to have exactly the same interface as the original one. So when you think about recursion, you have to start with, when do I stop the recursion? In other words, what question is going to be trivial when someone asks me, hey, this is a value that I need you to find in this array, and the length of this array is this long? What is going to be the easiest question? Let me see. Don't you think that's an easy one? The array has no elements. If an array has no elements and I'm asking you to find a particular value, what do you think your answer is going to be? False. Okay, well, that's an easy one. So to follow my own rule, I'm going to have result as a temporary variable. So in this case, we just say that the result is false. Confirmed. Okay, what else? In other words, how can we get to the else case? Well, we can get to the else case when length is non-zero, okay? And I should have chosen unsigned for length, because it really should not go negative. But, just assuming that no one's going to pass me a negative length to begin with, okay, what will get me to the else case? Length is greater than 0. It is at least 1, right? Well, if it's at least 1, I guess I have something to do, right? So over here, I'm going to say result is, there's always this lucky chance that whatever element the first element that I'm supposed to look at turns out to be what I'm looking at, what I'm looking for. That's always possible. Yay. Okay? In other words, think about Clint Eastwood as Dirty Harry. Okay? The first question is saying, do you feel lucky? Okay? Punk. Well, the punk may not be very lucky, but then the punk says, maybe my friend is. Okay? Because if the first element of the array that I'm responsible to look into does not have the value that I'm looking at, maybe it is in the rest of the array. Is that making any sense? So how do I formulate this in the same kind of question and pass it on to somebody else? I'm going to call find again. I'm not going to change the key. That would be kind of like defeating the whole purpose. But what I can do is I can change the array and also change the length of that array. Does that make sense? A is an array. It doesn't seem to make sense to add one to an array. But in C and C++, an array is a pointer, is an address. Exactly. So we're using pointer arithmetics to basically say the second element of my array is your first element. Okay? But then the length has to change as well because I have already taken care of the first element of this array. So the next person has one fewer element to look at. And this becomes the recursive version of find. So that immediately raises a question of, but why do we want to do it this way? This is so much longer. Well, I beg to differ. Because this is really just one way to express the recursive algorithm. The other way to express the same algorithm is like this. Okay? Int k, int a as an array, int length. So the other way to express it is to start with a return. In other words, we skip all the conditional statements and whatnot. We just start with a return. So the trick lies in the expression. Okay, the expression that we are returning. So we ask the question, is length 0? If that is the case, let's just return 0. If not, we'll return a bracket 0. Is my first element what we are looking for? If not, I guess now we will ask somebody else, is the rest of the array containing that value? So now I just have to match the parentheses, one more semicolon, and we're done. Recursion is cool. Because sooner or later, as a programmer, you may encounter a programming language that has no loops. So recursion becomes the only way of doing something repetitively. No one believes me. Who would write a programming language that has no loops, right? Yep. Huh? Lisp, Scheme, they're all like that. Most functional programming languages are like that without loops. Is that okay so far? So, recursion is important, okay? Very important. All right. So now that this part is done, we go back to our notes, and we are now done with this particular section. So this module is called counting. We are now done with it. Do we have any questions about counting? Nope. Okay. So if we don't have any questions about counting, let's see what's next. I think it's called events. So here's events. This one is really just terms for the most part, and it's coming from Wikipedia. I know a lot of professors do not like to use Wikipedia, but my take is, why do I want to reinvent the wheel and redocument something when it's already well documented? So what an event is it is just known as a subset of the sample space or the subset of outcomes. What outcomes are we talking about? Have we been talking about outcomes? I sure hope so, because that's what the omega is. Okay? So an event is nothing more than a subset of outcomes, okay, of all the possible outcomes. And in this particular terminology, sample space is the omega. Okay, so the omega generates the sample space. What are the possible outcomes from an experiment? And an event is nothing more than a subset of that. Okay, So in our terminology, okay, so let's switch back to the tablet. Oops, that's not the tablet. There we go. So in our terminology, if E is an event, E only has to be, so E is an event, then the only qualification to be an event is E has to be a subset of the big omega of some experiment. Okay? Well, that means we have a lot of choices for events. It can be an empty set, can be the entire omega itself, can be any subset of omega. So why do we care about events? The whole idea of an event is those are the things that you're interested in. Okay? Why do we need to know that? Because the probability of something happening, okay, so let's say the probability of a particular event is the cardinality of the event divided by the cardinality of omega. That is the probability of something that you're interested in happening. Okay, E, omega, those are all pretty abstract terms. Can we do this in a less abstract way? Absolutely. So let's think about this in a much more concrete way. Okay, so I will first introduce the omega that we are interested in as this. So it's going to be omega 5, and the set is 1 all the way up to 69. Cartesian product with the set of 1 all the way up to, is it 20 something? 26, I think. There we go. All right. We have talked about this a few times already. Why is that important? That's Powerball Lotto. Okay? We are looking at all the permutations of choosing 5 numbers out of 1 to 69 combined with a Powerball number of 1 to 26. Now, these are all in permutations. We are not quite cutting it down to combinations yet. Okay? But this is the omega. This is the space that we can generate. Is that okay? What event are we interested in? Well, that's up to your dream. Just like the Lotto website says, the first step is to dream, right? Or is it the second or the last step? I cannot remember. Okay, but once you dream and go like, I want to win the jackpot, okay? So now that becomes your interest. So your E, the set of all the outcomes that are of interest to you is the jackpot, okay? Now, to do this, we kind of have to do it in a kind of reverse way, because we kind of have to know what the jackpot is first, okay? And then we go back and figure out what is the probability of getting the jackpot, okay? So let's say we already know what the jackpot is. We know the jackpot has the following numbers. It has got 1, 16, 2, 18, and 50. I'm just pulling these numbers out of thin air. And we also know the Powerball number is 20. Okay. So now we have omega, being the entire space. We have the event being the possible outcomes of rearranging these particular values. So now the question is, what is the probability of winning the jackpot? Remember this thing here? The probability of winning the jackpot is now the cardinality of E divided by the cardinality of omega. What if you're not that ambitious to win the jackpot and you go like, well, maybe I'll settle for having 4 lucky numbers matching and and the Powerball number does not even match? Well, then it becomes a different problem, okay? What kind of problem do we end up with in that case? It's actually a little bit more complicated than it seems, but go ahead.
So you
we're only matching 4 of the 5 lucky numbers, and we are not matching the Powerball number.
So omega 4 out of whatever 4 numbers you chose?
Nope, it's not as simple as that. Okay. So, let me scroll up a little bit here. So this is for the jackpot. Jackpot. Okay. So let's say you're not interested in the jackpot. Let me go to the website first so I can point out which prize you're looking for. So we look for Powerball Lotto. It'll be pretty funny if those numbers actually match what I have chosen. But we know the chances of that happening already. So we go to how to play, but I'm looking for just the prizes, like what kind of prize you get. Okay, so we are interested in this one. Okay, so we're interested in only matching 4 of the 5 lucky numbers, not even matching the Powerball. Okay, and you can see the chances of this happening is a little bit bigger, and you get, but the prize money is not nearly as good as the jackpot. But still, I mean, close to $500, about $200 and something after tax. Yeah, not too bad. Okay, so now the question is, if this is what I'm looking for, what are the chances that I can actually win this particular prize? So now we go back to the tablet. Let me go like, so if I just want to match 4 lucky numbers and not matching the Powerball number, how many ways can we do this? Okay, what is the number of, in this case, we are still calculating permutations, but we know how to factor in the permutations later on. Okay, so the first question now is to ask, how many ways can we choose 4 lucky numbers out of 5? Well, that's an easy one. We know how many, right? So we know how many ways we can choose 4 numbers out of 5. So it becomes omega 4 trials without replacement. And this gets a little bit ugly, doesn't it? Because we're doing permutations where the ordering is important. Because the not so lucky number can be inside this thing here. So I have to factor that in. Well, we'll go ahead and do this first. Okay, 1, 16, 2, 18, and 50. So what we are looking at here, omega 4 of the lucky numbers, is how many ways can we choose 4 of the 5 lucky numbers? But that's not the number that we are looking for. This is a very small number. What we are looking for is a larger number. Because how many ways can we choose the non-lucky number out of the 5? Okay, let me ask that one more time. This will tell us how many ways we can choose 4 numbers out of the 5 lucky numbers, right? But your lotto ticket has 5 numbers. So that means this is only telling us part of the story. It's not factoring in the number of ways to choose a not lucky number, an unlucky number. So is that making any sense? So how do we know how many ways we can choose a unlucky number? There's only one unlucky number in this case because I have chosen 4 lucky numbers already. But what are those choices? It's going to be all the numbers minus the lucky numbers. Is that making any sense? So the first one, the omega 4, tells us how many ways we can choose 4 lucky numbers out of 5. The second row tells us how many ways we can choose one of the unlucky numbers. And these two have to be combined in order to tell us how many ways we can arrange to have 4 lucky numbers and 1 unlucky number. Okay, so you might think, oh, that's an easy one. We just need to do a Cartesian product. Because omega 4 is a set, omega 1 is a set. When you take the Cartesian product, it will give you 5 tuples, right? Tuples of 5 things. But that is not correct either, because out of those, it's always arranging the first 4 as lucky numbers, and the 5th one being the unlucky number. So now we need to think of ways to rearrange things. Okay, out of the 5 numbers, how many ways can we arrange the lucky numbers versus the not so lucky numbers? Now in this case, it's easy because it's just 5 times. So we are looking at this number times 5, because there are 5 ways to place that unlucky number amongst the lucky numbers. But wait, there's more. There's more, because we also have to think about the Powerball number cannot match. We are specifically targeting the price that does not match the Powerball number. The Powerball number in this case is 20. So that means everything in 1 to 26 except for 20 are available choices for our Powerball. So now we have to include the cardinality of that as well. So now we have to include the cardinality of choosing 1 out of 1 to 26 minus the actual Powerball number, and then look at the cardinality of that. So this eventually is going to be the numerator, and then we divide it by the denominator, which is the cardinality of omega, and that will give us the chances of winning the small prize money of $490, because you match 4 of the 5 lucky numbers, but you do not match the Powerball number. Isn't that ugly?
I think it doesn't work. It doesn't work.
It's usually not worth it, because otherwise people would just be buying. Oh. So, but this is the bottom line of the event. The E, the set of E, is basically asking what is of interest to you. And then you look at that, you divide the cardinality of E by the cardinality of omega, then you get the probability, you get the chances. Is that okay or not? Let's try one more time, one more example. So let's say this time you're over at a casino and you're betting on coin flips. Okay? You have already placed your bet. So let's say we have 5 flips. Well, let's say we have 4. Okay, I'm just thinking about how long that list gets. If I have to enumerate all the possible outcomes. Okay, so let's say there are 4 flips, and you're betting on, I think there will be 2 heads and 2 tails. Okay, that's your bet. So now the question is, what are the chances of your bet actually of you winning your bet? Is that making any sense? Yep.
Does order matters?
Hmm?
Does order matters?
Order is not important. Yeah, order is not important in this case. Okay. So what do? So let me phrase the problem here, okay, so that we know what we are dealing with. So we have what are the chances that 2 out of 4 coin flips are heads? That's the question, because you just put $100 on that. Is that okay? So what is the omega? In other words, this is an experiment of 4 trials with replacement, right? Because if the first coin lands on the head, can the next coin also land on the head? Yes, so it is with replacement. So what does your omega look like? The omega is going to look like head, 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 tail. Okay, head, head, tail, head, 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 tail, tail, Okay, I'm just going to forget about the parentheses because it's just taking me a lot longer to write with the parentheses and the comma. So I'm just going to write it without those. Head, tail, head, 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 tail, head, tail, head, tail, tail, head, head, tail, tail, tail. And then we have tail, head, 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 tail, head, head, tail, tail, head, tail, head, tail, head, tail, 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 head, head, tail, tail, head, tail, 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 head, and tail, 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 tail. There should be 16 of these. Let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Cool. So in my mind, I just equate head to 0, and I equate tail to 1. This is just listing all the numbers from 0, 0, 0, 0 down to 1, 1, 1, 1. Okay. If this is omega, what is my E? In other words, what is the subset of omega that I'm interested in? Well, I only want 2 heads out of 4. So that's going to be tail, tail, head, head, tail, head, tail, head. Okay. Head, tail, tail, head. Head, tail, head, tail. And head, head, tail, tail. I'm pretty sure I'm forgetting something here. Tail, head, head, tail. And what else am I missing? Okay, I think I got everything here. Yep. I think we got everything here. So what is my odds? What are my chances of winning that bet? What is the probability? Is the cardinality of E, which is 6, divided by the cardinality of omega, which is 16. 6 divided by 16, that's my odds. It's a little less than half, but not too bad. Is that making any sense? So are we good so far? Okay. So this is a really good segue to the binomial distribution. Okay. In other words, okay, you look at this. Does any of this remind you of binomial in mathematics? Yes or no? No. Okay, I like that answer. Yes. Okay, I like that answer too. Okay, because we want to look for these hidden patterns. Okay, is how does coin flipping has anything to do with binomials? Let's think about it. So forget about this slide. Instead, we are now talking about binomials. So we say x plus y to the power of something. That's 2 here. Let's put a 2 here. Do you think that relates to binomials? Yeah, it looks that way. Okay. Do you think, let me change this a little bit. Do you think that is still related to binomials? Yeah, anything we have a summation of 2 things and then the whole thing to the power of something is a binomial kind of question. Okay, all right. So when we spell this out, what does it look like? In other words, you use the distribution. Okay, you use multiplication and you use a distribution of multiplication over addition, and you spell out every single possible term. What do you end up with? Well, let's think about it. Okay. Is that one of these? One of the things? Okay. The next one, can we have x times x times x times a y? Sure. Can we have x times x times y times x? Yeah. I mean, I sure hope so. Can we have x times y times x times x? Yeah. Can we have y times x times x times x? Yeah, okay. Okay, next, let's move on to 2x and 2y's, right? Can we have x times y times y as a component? X times x, whoops, back. X times y times x times y. Sure, x times y times x. Okay. I mean, I really hope that you guys are seeing where I'm heading because this is getting really boring. Can we have x times y times y? Okay. Huh? I already have it? Oh, okay. So we're done with all the x's now. So now we can start with all the y's. Can we have y times x times x? Y times x times y times x? Y times x times y. Yeah. Okay. Do you guys want to be even bored any further? Let's do that since we're this far already. Might as well. Okay. So let's think about all the ways to have 3 y's and 1 x. So we can have y times y times x, y times x times y times x times y, and x times y times y. Okay? And the last one is just 4 y's. Okay? There's only one way to have y times y times y times y. So if you expand out this binomial, it just looks like this. Yes? Does it vaguely resemble something that we have seen a little bit earlier? If you equate x to head and y to tail, doesn't that remind you of something that we have seen earlier? So now can we relate, experiments involving flipping coins to binomials? Yeah. Cool. But wait, if it does relate to binomials, that means Pascal has something to do with it, right? I hope you guys still remember Pascal's triangle. Or has everybody been exposed to what Pascal's triangle is? Okay. Well, what does that do? Okay, we can construct Pascal's triangle first, and then we try to see what it means, okay? So Pascal's triangle starts with a 1, and then we have 1, 1, and then 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and so on, okay? How do we come up with these numbers? Well, it's addition, right? So along the edges of the triangle, they're all 1s. Okay, so we already know the next row starts with a 1, ends with a 1. And then in between, each number is the summation of the 2 numbers that are quote-unquote on top of it. So we have 1 plus 4, which is 5, 4 plus 6, which is 10, 6 plus 4, which is a 10, 4 plus 1, which is a 5, and so on. I don't see any relationship between the binomial, expanded form of the binomial, and Pascal's triangle. Let's do some counting here, okay? So let's count all the terms that can be combined because they really end up with the same value. Can we combine x to the power of 4 to anything else in here? Assuming that x can be anything, y can be anything. Nope, x to the power of 4 is kind of on its own. What about x times x times x times y? Can we combine it with something else? Yeah, because it's the same value as x times y times x, which is the same thing as the next one and the next one. And there are 4 of those things, right? What about when we are only interested in x squared times y squared? How many of these things ends up to be x squared times y squared? There's 6 of these, okay? 1, 2, 3, 4, 5, 6, okay? How many things, end up as y cubed times x, or x times y cubed? 4 of those, 1, 2, 3, 4. And how many things ends up as y to the power of 4? Only 1. So we got 1, 4, 6, 4, 1. Wait, we have seen that right here. That's how we relate binomials to Pascal's triangle. In other words, Pascal's triangle is giving you some idea of what is the quantity of the combination of the x and the y, powers of x and powers of y. Yep.
Word to the fifth, the next row, 1, 5, 10, 10, 5, 1.
The next row.
If you did.
Oh, x to the power 5. Yes. Yep. So now the bigger question is, what about these numbers? I mean, if I want to figure out, like the nth row and then the mth item on that row, do I really have to fill up the triangle to figure that out? Or is there a faster way to get to it? And of the grand scheme of things, how does this have anything to do with combinations? So those are the questions that I want you guys to think about and read, because they're all in the modules before the next class. And I'll show you where in the modules we are talking about. Okay, so those are all in I think in discrete probabilities, but it can also be, yep, I think they're all in discrete probabilities. Let me just double check before I turn off the recorder, because then I can say, yep, I said that. Yep, they're all here. So they're all here, okay? So we want to understand what is Pascal's identity, what is the binomial theorem, and in this case, how is it proven by induction, okay? So that's what we'll be talking about on Wednesday, okay? So you got about 6 hours and a half to do your homework assignment.
So I looked at the submission for that question, and it said I didn't have an answer for it.
Oh, that could be wrong because I forgot to upload some of the PDFs